Working with plane mirrors will take us back into our idea of the principle of least time that I mentioned in my notes for the first two learning objectives of chapter 23. Suppose I have some source that's located at point A. And I, or well, whatever, suppose you're standing at point B and you're looking at the mirror. Well, so the mirror has specular reflection as opposed to the diffuse reflection of, like tabletops, books, the person next to you. Now, where is this person going to see that? Okay. There are two things that define this. First, I could do this mathematically. With the principle of least time. Basically, if I've just got one, like here is some medium through which the light is traveling, medium 1. Now in this case, we're looking at a reflection, so we're looking at this medium 2. Whatever this might be, doesn't matter. In fact, in some cases, it could. If we have like a sheet of glass, if you're looking at a glass tabletop, some of the light is going to go into medium 2 and stay there. Some of the light is going to reflect on the surface. Here, we're just looking at a reflection. So let's say that for right now, no light actually moves through medium 2. According to the model we use, we're going to have like some fake light, some virtual light that's there to help us track where we see the image. But no actual light is in this space. Now, I have that, and I have the law of reflection. When I have light interacting with a surface, then I have some incoming light. Now, what I'm going to do is I'm not going to define the light in terms of the surface. I'm going to draw a line, actually that normal, like kind of an old version for normal, or perpendicular to the surface, and define that light by the normal. That's theta, or angle, sub I. So theta sub I the angle of incidence is equal to the angle of reflection. Now, that also gives us a reason as to why the normal is most useful. Because if this is like a rough or a curved surface even, it could be hard to define that surface. But it's easy to define the normal. If I don't have a usefully reflective surface, but let's pretend the whiteboard is. Suppose I've got a nice solid beam of light as coming from a laser pointer. Now if that was reflected, I'd have light going in, and then for some part of it's reflecting off at an equal, or the angle of incidence, the angle from this beam, and these are whiteboards, I can't just pound them together to get a cloud of chalk for this to move through. But as this beam comes in, then it will reflect off at the same angle to the normal. The reason why this is helpful to use the normal instead of the surface is because suppose I take this and I move this around. If I've got the beam of light traveling on a path that's normal to the surface, then, that angle of incidence would be 0 degrees, which means that the angle of reflection would be 0 degrees, which means it would bounce back up the path, and I could see the reflection really close to, or on, so to speak, the source. Conceptually, it's easy to imagine working out how would I find out and define where the normal is. Now, with these requirements, what's going to happen is that these are going to strike such that the angle of incidence is equal to the angle of reflection. Now, let's say that I'm looking at a variety of different places, so I'll put a couple more paths on this list. Now for each person, each point, I'm seeing like, oh, okay, the light appears to be coming down this path, which means that because that light doesn't know anything now about the existence of any sort of, what happened to it before it bounced off of this case. If I track these points back, the image is going to appear to be that same distance beyond side. If this appears to be, say, 15, if I've got a bright point source A that's 15 centimeters away from the mirror, the bright point source is going to appear to be 15 centimeters below the other side of the mirror. To put it a different way, if I've got a person who is standing four feet away from a mirror, then the image that's formed in the mirror by light bouncing off of that person will be 4 feet behind the mirror. So if you stand 4 feet in front of a mirror to comb your hair, you look like you're doing that with the assistance of a person mimicking you who is 8 feet away.